Hello students, welcome to lecture number 10 of Computer Architecture course. The topic of today's lecture is MIPS Datapath instruction flow, and we will focus on the actual interconnectivity information of the MIPS Datapath in this particular lecture. So far, till the previous lecture, we were focusing on the individual components, their individual functions, their bit width information, and how they play a crucial role in performing individual operations of an instruction. We are going to add up everything together in this particular lecture, and you will see the greater details of MIPS Datapath in this lecture session. Okay, so let us get started. So let us start with the instruction fetch unit. So what is an instruction fetch unit? The instruction fetch unit has three major blocks. First is an instruction memory, second is a program counter, third is an instruction for next address logic. Okay, so what I basically would like to mean here is that the next address logic block is responsible for computing the address for those type of instructions that deals with branching and jumping. Okay, we'll build the internal block and circuit for this next address logic also. PC, program counter, as I explained earlier, also is responsible for providing the address, okay, for the next instruction, and instruction memory will actually provide the instruction word, okay, which is 32-bit size. So let us start with add sub instruction, which is R-type instruction. So in the R-type based instructions that deals with add sub type instructions, you have a 6-bit opcode, 5-bit RS field, 5-bit RT field, 5-bit RD field, 5-bit shamed field, and 6-bit function field. Okay, using this information of the bit fields in the R-type instruction format, we can actually build a data path around it. Okay, so you have a 32-bit register file, right? You have a 32-bit register file, and the inputs are RW, RA, and RB. As I said in the last lecture, that RA and RB are used for selection of registers to place the data onto the bus. So RA comprises of the information that comes from RS field, which is 5-bit. RB comprises of the information that comes from the RT field, which is 5 bits, and RD is a destination register, that is the one which is used for RW, which is also 5 bits, and the bus W input, which is 32-bit, is actually the input that gets into the register for storing or writing the data into the register file. The output of this register file goes directly into an ALU, each of which is 32-bit, and finally we produce a result. Okay, so this is a high level overview of how we handle add sub instruction using R-type instruction format. Right, so every input RD, RS, and RT are 5 bits. The input for writing the data is 32-bit, and the outputs of the register file is each 32-bit for bus A and bus B. And finally, the output of the ALU is also 32-bit. So we know that RA, RB, and RW comes from RS, RT, and RD fields of the instruction format. What about instructions with immediate field? Okay, let's take two examples. We have LW $T1, $0 $S1, and then we have ADDI $T1, $T1, 3. The upper half of the 32-bit register file, where you have a mux that comprises of two inputs, which is RD and RT, is because of the following reason. Okay, for example, if you have an R-type instruction format, the destination field is RD, while if you have a load store type format, okay, or let's say I-type format, then the destination field is RT. So therefore RW gets the input from the output of the multiplexer, while the input of the multiplexer can be either of the two, which is RD for R-type instructions and RT for load store type instructions, which is a destination field for both. And it is of course controlled through a select line, which is governed by a control signal, which is reg DST. Now the output of this gets into the ALU, as you could see in the figure, this bus A I'm talking about, that gets into the ALU. The second bus, okay, which is the output of the register file, gets into a multiplexer. So this is the second switch. This multiplexer has two inputs. One is the output of the register file, and second is the input of the immediate 16-bit value. But if you recall, in the last lecture also I said that 16-bit value cannot be fed directly into the mux, because we need to pass it through a sign extension unit or zero extender unit that adds up zero values as a padding to make it look like a 32-bit value, and that 32-bit information gets into the mux. So this 32-bit information is one of the inputs of the mux, and the other 32-bit information is the output of the register file that gets into the multiplexer. So this immediate field is for target address calculation, right? And once you pass it into the mux, so the output of the mux will either be the direct value from the register file, which is 32-bit, or it will be sign extended immediate field 32-bit value. So as you can pretty much comprehend that this multiplexer here is used for selecting between register computed output or for target address I type. For either of the two, this mux is providing the value into the ALU, because the ALU can perform both the things. It can also compute between two registers, or it can also compute between a register value and add the 16-bit immediate field sign extended to 32-bit to compute the effective address of an instruction. And once that effective address is computed, then that information is now fed into a particular block from where the data will be written back into the register. So that's why we have this information going here into the register file. Although it doesn't go directly here into the register file, there are certain blocks here that will be responsible for doing some operation, and from there it will actually go into the register file. Okay, so this is the one that is used for selecting between LW destination and destination of arithmetic type instructions. This is used for execution and computation. This is used for selecting between register computed output and target address. And this is the sign extension place, sign extension unit that extends 16-bit to 32-bit. Now let us have a look at the load instruction. What if you want to execute a load instruction through the MIPS datapath? You see, you have an ALU here. The output of the ALU is 32-bit that goes into the multiplexer, and you also have a data memory. Okay, this data memory comprises of 32-bit information. Okay, and it's governed by a clock that you see here. So the input of this multiplexer could either be the output of the data memory, or it could be the output of this ALU. So this ALU is actually trying to produce the output after computation from the ALU based on two registers, or registered and a constant. In this case, it is the output of the data memory when we want to load a particular data from the data memory back onto the register. Okay, in case of LW instruction load. Because for example, if you look into this instruction here, from the effective address computed between the offset and the base address, it gets to a particular location. From there the data is loaded into this register. So that is exactly what we are doing here. From the data memory, okay, we will load it directly into the register file RW, in that RW register, 32-bit information, and the address is also coming from the ALU, right? So the ALU can of course compute the address also, if in case we are using data memory. If we are not using data memory, then it can directly go into the multiplexer, because we are computing upon two register contents or register and a constant. Okay, so this data memory is for loading data from memory to register values. Okay, now let us have a look at the store instruction. So you see here, the upper part of the block has already been explained, right? You know RW, you know RA, RB. So I'm not repeating this thing. This part of the block is now already known. In case we want to store something from the register into the memory, so this part of the wire that gets out of the register will be directly fed into the data memory, because we are writing a value into the memory, right? So this part of the connectivity is reflecting the bypassing information of the mux for directly writing data into the memory here. So this goes here. This data memory is where the data is being stored based on the SW instruction that you see. And this part of the information which is reflecting the address of the data memory is being computed by the ALU in case we want to know where is the location where the SW instruction has to store the data from the register into the data memory, right? So we also need to know the address. Without knowing the address, we cannot store it onto a particular location in the data memory, right? So you see in this particular piece of block of the piece of hardware of the MIPS 32-bit architecture, there are three important things to note. The first is that the bypassing is done here before the multiplexer, because the value from the register is going directly into the data memory. Okay. Second is the address is being computed based on the ALU output. Okay. So that is the effective address calculation that is being done based on this offset value and the content of the register, which is a base address. And this is the place where the data memory actually stores the data based on the SW instruction from the register. So this write enable is kept at 1 when we want to write the data into the data memory. Fine. Okay, now let us have a look at the branch operations. This is very, very important. So in the case of branching based operations, which are part of the I-type instruction formats, we have to first know this particular function or formula for evaluating the immediate or target label. In case of branching, the immediate or target label is given as target address minus PC plus 4, whole thing divided by 4. So therefore 4 into immediate plus PC gives you the target address. So we know that target label and target address are not the same thing, right? When we have a BQ and then we have R1, R2, L, then we know that L is actually talking of the target label but not the target address. The target label is just giving a pointer to the address, and of course target address is computed based on the value of the 16-bit immediate field. Actually it is sign extended to 32-bit, so we can say 32-bit immediate field multiplied by 4 plus relative updated PC plus 4, and that together gives you the target address. Now going by this function that you see here, the next address logic, okay, which is the block that you had seen in the second slide of the stock, is the block that is being expanded here internally. So how does it work? So you have 4, because of 4 bytes, you have the PC. So this gives you PC plus 4 here at the output of this adder, and that PC plus 4 is again fed into another adder and added with immediate field 16-bit PC extended, or in other words we will extend this to 32-bit sign extended, which I already had said. So this becomes 32-bit here. So that 32-bit is the one that I'm talking about, this immediate field here, and this becomes PC plus 4. So these two are added to produce an output. So one important thing to note here is that we have not really multiplied this immediate field with 4 after we do the extension, but here there has to be another unit in the real data path that computes the shifting of that particular value by 2 bits to the left, so that we can achieve the formulation of 4 into immediate that we want to target. So 32-bit multiplied by 4 gives you the value which you see in this portion. That being added with the PC plus 4 gives you the value of the target address for branching. So the mux either selects between PC plus 4 in case of regular instructions, or chooses between the branching address, which is 4 into immediate plus PC plus 4, and that output is again sent or stored into PC, and that becomes the value of the updated PC. So that is again sent back here, and if that is used as an address, then from there we will feed it directly into the instruction memory from where the instructions will be fetched, right? So by looking at this diagram, you can clearly make out that we have two different adders. We have a MUX, we have a sign extender unit, and we have a PC, and the output of the PC goes into the instruction memory from where the instruction will be fetched, right? So this is pretty much clear. Now if you want to merge all the units together, okay, so the MIPS 32-bit architecture would look like this. So this is where the final block diagram almost would be looking like. Okay, this is almost pretty much the final MIPS 32-bit architecture, although we'll do few more enhancements and modifications and improvisations to this Datapath hardware also, but this is pretty much the penultimate diagram that you can think of. Okay, so let us try to understand this well. So this gives you all the details necessary. So you have the instruction memory, which has the read address from the program counter. You have the output, which is the instruction that it is fetching from the instruction memory. The value of that will be 31 down to 0. Note it. Okay, the input of the PC comes from the output of a MUX. Okay, so we'll talk about this input of the PC a little later. Let us gradually move in and assume that the PC gives the value of the address. How the value is calculated, we'll get to that little later once this part is over. So let us imagine or assume that we have the address available with us. Okay, so once this address is available with us, we will feed that into the instruction memory and we'll get the instruction. The instruction 31 down to 0 can be further broken down into the following form. Instruction 25 down to 21 is talking of the RS field, which is actually the one that gets into the read address one, okay, of the register file. RS field 25 down to 21. The next is the RT field, which is 20 down to 16, which is the second register value that is being sent into the register file. Now that is also transferred into another multiplexer here. Why is this multiplexer here? I had already spoken about that, because in case of writing, okay, in case of the writing, the destination register in case of R-type instruction is RD, okay, and that RD is 15 down to 11. So this is in case of R-type instruction, which is 15 down to 11, that goes as one of the inputs of the MUX. But in case of I-type instruction, the destination field RT is 20 down to 16. So that is also the another value of the register that has to be fed into the multiplexer. So multiplexer of the write register value or write register number can be the RD in case of R-type or RT in case of I-type. So RD in case of R-type is 15 down to 11 from the instruction format, while it is 20 down to 16 in case of I-type format, because it is reflecting the RT field. Okay, so that's why we have a multiplexer here. Okay, so these three are clear. Now let us move further. The register file has read data 1 and read data 2 as the two outputs. The read data 1 goes into the ALU. The read data 2 gets through to the ALU through another switch or multiplexer. Here this multiplexer has one of the inputs from the read data 2, and the other input is coming from the 15 down to 0 field of the instruction format in case it's an I-type instruction, and that will be sign extended to 32-bit from 16-bit and fed into the multiplexer, right? So as I said you earlier, that the ALU is responsible for computing between two registers, or it is also responsible for computing between a register and a constant, which is 16-bit extended to 32-bit, or it is responsible for computing the effective address between the offset that we get from this field, which is the immediate field, sign extended 32-bit, and adding the source register, which is RS basically, right? So that's why the ALU has a multiplexer here at the second input, coming from directly from the register file and second coming from the immediate field, and that acts as the second input. Once it is done, it goes into the data memory, right? It goes into the data memory. Now in case it's a load type instruction, now we know that in case of load type instruction, it's the effective address that is being computed. Now since it is effective address, so this gets connected to the address of the data memory, because the data memory needs the effective address from where the data has to be loaded. So this is connected to the address part. Okay, while it is also possible that we can totally bypass this and we can have the direct computed value, okay, of the ALU to be fed into another multiplexer, because we may not be always working on LW. So this could be a direct ALU output based on the computation of two registers in case of arithmetic operations. So that is another possibility here. So therefore we have a bypassing of this unit totally, and this gets connected to this multiplexer, while the other input of the multiplexer could be the read data of the data memory, which is the data that we want to load from memory in case of LW. Okay, so therefore we have two different types of inputs here in case of this multiplexer. Another thing to note here is that if it's a store type instruction, then we will directly store the value of the register into the data memory. So we also need another input which is known as write data, because sometimes we also may need to write the data into the data memory. So this write data is nothing but the input coming from the read data connected to it directly. Fine. So this register file is clear, this MUX is clear, this ALU is clear, and this data memory I assume is clear, and this multiplexer is also clear. So pretty much everything in this line is now clear, and also you now know what is the role of sign extension. So now let us move forward to the next step. Once you have this multiplexer ready, then the output of this multiplexer, which may contain the data of the data memory or may contain the output, okay, of the ALU, that has to be now written back into the write data field of the register. Which register is specified by the register number, which is given by the destination register number, either which is instruction 15 down to 11 referring to RD of R type, or 20 down to 16, okay, which is referring to RT of I type. That's how we get the number of the register, the specific number where which register it will be written onto. The data of that will be either gotten from the data memory or directly from the ALU, which is connecting back to the write data. So this is also now clear. Now let us move forward to the next block. What is the role of this ALU control? This ALU control has an input which is instruction 5 down to 0. Now this 5 down to 0 is referring to the function field of the R type format. Funct, F-U-N-C-T, funct field or function type field of the R type format, which is 6 bits usually. So that tells the ALU what type of arithmetic operation has to be computed, whether it has to be an add type or subtraction type. Okay, so that's why this is also important. So we have a second ALU control here, okay, because there is already a major ALU control here. So this is a second ALU control. I'll get to this later. So this ALU control is actually helping you to tell what type of arithmetic operation has to be done. So because this function field 6-bit, which is instruction 5 down to 0, tells you based on the value whether it's an add or a subtract. So okay, so that's why this has to be fed into the ALU as one of the inputs. So now we see that this instruction memory block, the 3 consecutive multiplexers that you see here, this register file, this ALU, this data memory, ALU control, sign extender, everything is clear. Now what is the next thing? Okay, now imagine you want to do, now let's get back to the PC thing. Okay, now imagine you want to do a branching. Okay, in case of branching, we compare the values of the two registers to see if they have an equal value. So if they have an equal value, right, so we need a 0 flag to flag on or turn the flag 1 in case they have equal value. So that's why we have a flag called 0 here that turns on when the BQ instruction results into equal value for both the registers. So in case the registers have equal value, so this becomes 1 and that gets onto one of the AND gates. The other AND gate input comes directly from the centralized controller. That's why we have a branch here. Okay, so this is the role of this AND gate here. And as I was saying, that in case you want to now perform the or compute the effective address of branching, then it will be 4 into immediate plus PC plus 4, right? That is how it was formulated, isn't it? 4 into immediate plus PC plus 4, that gives you the target address. If that is the target address, then once we have a 32-bit sign extension, that has to be now sent into a left shift unit by 2 bits in order to have an effect of multiplying by 4. Once it is done, then that is added with the PC plus 4, right? Because 4 into immediate thing is accomplished here at this output, added with PC plus 4 gives you the value of target address of branching. So that could be one of the inputs of this multiplexer. The other input of the multiplexer could be the regular PC that you have, okay, in case it's not a branch. So based on whatever it is, okay, based on the select line value, whether it's a branch, if it's a branch, then of course we will have to set this. If it's not a branch, then this has to be set. So depending on whether it's a branch or not, the new PC is computed and that is fed into the input of the program counter block. Okay, that's how the next address logic works for program counter. And once you know what the address is, it supplies the address into the instruction memory, and from there the instruction is fetched onto the next half of the or next stage of the data path unit. So this is pretty much clear. Now the last block that is pending here is a control unit. Now this control unit is actually controlling the entire data path. So everything that you see in the data path except this red color block is the data path unit, and this is called centralized controller. So centralized controller is sending signals to almost everything, to this AND gate, okay, to the register file, to this multiplexer, to the memwrite, which is the data memory, to the multiplexer here, which is mem to register, to the mem read, which is also helping you to read the value, okay, in case we want to load it from memory into the register. It is also controlling the ALU operation, which is this one, okay, that is also being controlled by this. It controls the select line of this multiplexer, which is the first one that chooses between the destination registers. So this is the controller that is actually controlling, enabling or disabling and helping in timing synchronization of the entire data path. Okay, what will happen when is controlled or decided by this controller. Okay, so this is the pretty much the penultimate MIPS data path that you see, that handles almost every instruction in MIPS 32-bit architecture except one, okay, except one instruction, and that we are going to speak in the next slide. You see in the slide everything that was there in the last slide is here except one unit that is being added, and that unit is this extra multiplexer that we have. So instead of 1, 2, 3 and 4, now we have 5 switches in this circuit. We have 5 multiplexers. So this last multiplexer that you have, that also performs a crucial function, which is the MIPS data path with the provision of jumping. What if you want to calculate the effective address of jumping? How will you do that? So this helps in that. So what is the process? First of all, let us recall what is the process, or what was the process of computing the target address of jump instruction. If you recall, the upper 4 bits of the current PC plus 4 is concatenated at 31 down to 28. The 26 bit of the immediate field of the jump instruction and the lower order 2 bits will be all 0 0. So that is exactly what we are doing here. In this output which we already have, so this could be one of the outputs of the branching or regular PC, and the other input of this multiplexer will be this, which is coming from the left shift by 2, because we have another shifter here. So this is the 26 bit field, which is 25 down to 0 as per the J-type instruction format, which is reflecting the address, and that will be left shifted by 2 bits. That means we will append 2 zeros in the first 2 bits, and that gets you to 26 plus 2 gives you that 28 bit. So left shifting by 2 bits makes it 28 bits, and then we also concatenate the PC plus 4 at the 31 down to 28 field. So this is becoming 0 or 27 down to 0, and 31 down to 28 will be the output of the PC plus 4 that has to be concatenated with this 0 to 27 and then 28 to 31, which is 31 down to 0 in totality, giving it a 32-bit target address of the jump which goes into this multiplexer, right? So this is the PC plus 4 that gets appended or concatenated at the place which is 31 down to 28, and this, after left shifting this 26-bit instruction address field, it becomes 27 down to 0. So 27 down to 0 and this upper order 4 bits, 31 down to 28, gives it 32 bits. That is another input of this multiplexer, and this output then again connects back into the program counter. So now the program counter could have a value of PC plus 4 or could have a value of PC plus 4 plus 4 into immediate, giving it a target address of branching, or it could be the value of the jump which is given by this process which I just spoke of. And this multiplexer is also controlled by the centralized control unit through a signal called jump. Okay, so the two new units that we have added here is this extra switch, extra multiplexer, and this left shifting unit. Okay, and of course this extra control signal. So this MIPS Datapath with jump is effectively the Datapath processor of MIPS that is existing in many of the processors that you see for many niche applications, as well as in several applications of general purpose nature of RISC based architecture. Now let us have a look at what are the major control signals in MIPS processor. The major control signals, if you look, that is sent by the MIPS controller into the MIPS Datapath are reg write, ALU SRC, branch, mem write, mem to reg, mem read, reg DST, ALU operation, jump, and PC SRC. So keep in mind these are the major control signals that are sent by the MIPS controller into the MIPS Datapath. So in the MIPS Datapath, we see that it has 5 basic stages: instruction fetch, instruction decode, execute, mem, and write back. The instruction fetch is responsible for instruction fetching and updating the PC. The decode stage is responsible for instruction decode, register read, sign, extend, offset. Execute is for executing R-type instruction, calculating memory address, branch comparison, branching, and jumping calculations. The mem stage is responsible for memory read, memory write completion, R-type completion, and finally the WB, which is the write back, is responsible for memory read completion, because we want to load from memory by reading it and then write it back into the register, which is reg file write. Okay, so this is a summary, and usually we will consider that each of these stages take roughly 1 cycle. So in 5 cycles every instruction gets completed. Okay, now once things are done in parallel, there could be several interlocks and hazards that may come into the play, due to which it may not complete in 5 cycles, and that we are going to look at in the next lecture. Okay, so we are done with this lecture, and in this lecture you would have learned several things about MIPS Datapath, starting from the overall connectivity, starting from the interconnectivity of each of the blocks, how to calculate jump, how to calculate jump target address, how to calculate branching target address, how to do that using hardware. Okay, what are the major control signals, what is the role of the different switches. You've learned about 5 different switches or multiplexers here. Okay, you've learned about centralized control unit and a sub controller which is known as ALU control. Okay, so everything you have seen, and what are the bit field size. So in this lecture we have pretty much covered about the MIPS Datapath. In the next lecture we will focus on MIPS instruction hazards, that is how the interlocks get controlled, or how we can arrive into an interlock condition and how to resolve those issues. Okay, thank you so much.